Hi, so we've already looked at centripetal force in horizontal systems. Now let's look at it in vertical systems. As was the case with vertical spring block oscillators, it's going to be a little bit more complex. And in this case, a bit more complicated. But you know what? You're up to the task. It's nothing new. It's just is presenting things in a slightly different way. So let's get on it. Okay. The first bit of advice I have to you when solving vertical centripetal force problems is to set the center of the circle as the positive direction. Don't say up is positive. Don't say right. Don't say the direction of motion. Say the center of the circle is positive, and it will make life a lot easier. So here I have a person going around in a circle on this vertical track. When they're at the top, their weight, their mg, is pointing towards the center. That's a positive value. But that same person, when they get to the bottom, now their mg is pointing towards the center of the earth, not towards the center of the circle, in the opposite direction. So therefore, it's got a negative value. Now, another thing we have to keep in mind when dealing with vertical circular motion is that the centripetal force is always going to have a gravitational component to it, or at least it usually will. So let's look here. So if I'm at the top, the centripetal force that's causing me to travel in a circular path is going to be equal to mg, which is pointing to the center of the circle, and the normal force, which they're both pointing towards the center of the circle. So these two add together to give me my centripetal force. On the other hand, when this person reaches the bottom, mg is pointing away from the center of the circle. So now the centripetal force that I'm experiencing is going to equal the normal force, which is pushing towards the center, minus mg, which is going the opposite way. And as a consequence, we see the normal force has to get bigger. And if I'm going up the side, so I'm halfway up, what I find is the normal force is still pointing towards the center. It always does in a case like this. And mg is at a right angle to that. So in this case, the centripetal force is simply equal to the normal force. Now, we're often asked to calculate what is the minimum velocity needed to complete a circular path. So we're given a case of like a person on a roller coaster, and the roller coaster is going to go over a vertical loop, and we want to know what is the minimum speed needed to get there. So please pay attention here because I'm going to try to get this explained conceptually, and hopefully it will help. So let's just say I start off with a velocity that's significantly greater than what is the minimum necessary to go in a circular path. So I have a very large velocity. So that means I'm going to have a lot of centripetal force, and that force is going to equal to mg plus my normal force. And since I have a lot of centripetal force because I have a lot of velocity, I've got a lot of normal force. But if I go slower, what happens is my mg is not going to change. So how can my centripetal force go down? Well, the normal force. I'm being pushed less force by my seat. I'm feeling lighter in my seat, but I'm still above that minimum. When I reach that minimum, what defines that minimum is this: when the normal force, or in the case of something like strength, the tension force, goes to zero, and the only force causing centripetal force is mg. That's the least I can have. So the smallest velocity you can travel and still go on a circular path is when your entirety of your centripetal force is coming from mg. If you travel at less than that minimum value, you are not going to travel in a circular path. You're going to go into a parabolic path and fall off the tracks. And that's not going to go well for you. So how do we find the minimum velocity needed to continue in a circular path? It's pretty easy to derive, and it's pretty cool once you do. So let's just go through it real quick. All right, so centripetal force is equal to mv squared over r. There are two forces acting on this object. That's mg pointing down and the normal force pointing down. Remember, we're trying to find at the top, okay? And the combination of those two give me the centripetal force is going to be my mv squared over r. But remember, the minimum is going to happen when the normal force goes to zero, and the only force causing centripetal force is mg. So that this then collapses just mg equals mv squared over r. And I apologize that these m's look different. Let's just pretend that this is the gravitational mass, and this is the inertial mass, and they're the same thing. So they just cancel out, give me g equals v squared over r. And if I solve that for v, I get v at the top. The minimum speed at the top is always going to be equal to root gr. Pretty sweet. Now, here's the thing. You can derive this when you need to know this. Not that hard to do, really, apart from remembering, that you have to let the normal force go to zero, or you can simply memorize this. I'll leave it up to you. I don't memorize it. I just derive it each time. Okay, so let's look at an example of a roller coaster that's traveling 8 meters per second. It reaches the top of a 16-meter tall circular track. Will the cart remain on the track or not? So the first thing we have to keep in mind is I don't really care what the height of the track is. I care what the radius is because that works in my equations. The radius of a 16-meter high track is going to be 8 meters. The next thing I would do, I was going to say, well, I've memorized or derived that the minimum speed necessary at the top to stay in a circular path is root gr. and that would be root 80, which is 8.49 meters per second. And unfortunately, you're only traveling 8 meters per second, so this cart is not going to make it over the circle. It's going to fall. If it was going greater than this, if it was going this, it would make it. If it was going greater than this, it would be at a faster velocity, so there'd be some normal force in addition to gravitational force pushing on me. So remember, at the top of the circle, both gravity and normal force are acting in the positive direction to produce my centripetal acceleration. So I say Fn plus mg equals mv squared over r. So when I solve for the normal force, I get the centripetal force minus mg gives me my normal force. And that's why you feel a bit lighter at the top, because your weight is basically pulling you away from your seat. Whereas, oh, no, we're going to do that one later. Okay, so let's just look at how we would calculate what is the normal force acting on a person traveling 12 meters per second when they reach the top of a 16-meter high circular track. And I want to know what is the normal force acting on that person. So what I would say is centripetal force equals mv squared over r. I have two forces acting on that person. I have mg plus the normal force is going to make my centripetal force. The person is 60 kilograms, so that's 600 newtons of gravitational force plus the normal force is going to equal 60 times their velocity squared over the radius. And when I solve this, I'm going to get 480 newtons, which, if you think about it, when the person is just sitting there waiting for the ride to start, since they have 60 kilograms, the seat would be pushing upwards on them before it started with 600 newtons. So at the top, they're going to feel lighter than they would normally. Now, when you reach the bottom of it, what you're going to find is that the gravitational force vector is pointing in the negative direction with respect to the center of the circle. So what I'm going to get there is the normal force minus mg equals mv squared over r. So when I solve that for the normal force, what I'm going to find is it's going to equal whatever the centripetal force is plus mg. That's why you feel heavier when you get to the bottom, sometimes significantly heavier depending on how fast you're going, because a lot of times going from the top of the roller coaster to the bottom, you're going to pick up speed, so it can be significantly greater at the bottom. Okay, so how do I go about finding the velocity at the bottom of a roller coaster when I'm at the top? Okay, so often we want to know what changes happen between the top and the bottom, bottom and the top. So the way we solve this is using conservation of energy. Things have a tendency to tie together in AP Physics 1. So remember, at the top here, the person has two forms of energy. They have gravitational potential energy, mg delta h, and they have kinetic energy, 1/2 mv squared. And we'll designate that v as v top because the speed at the top and the speed at the bottom are going to be different. And what we're trying to find is the speed at the bottom. All right. So what's going to happen is they're going to have all of this energy converted entirely into kinetic energy by transforming this into their kinetic energy. So the first thing I'm going to do is I'm just going to get rid of all the m's. They just get in my way. So what that leaves me with, g, and my height is going to be twice the radius. So instead of calling it h, I'm going to call it 2r. So I have g 2r plus 1/2 v top equals 1/2 v squared bottom. Did I say v squared? I meant v squared. Okay, so that means I've got 4gr is equal to, because I'm gonna multiply both sides by 2 to get rid of these halves. So that gives me 4gr plus v squared top equals v squared bottom. So if I just take the square root of that, that gives me my expression for what the velocity is going to be at the bottom. Now I'm going to substitute in the values. So I have 4 times g is 40. The radius is 8. The velocity at the top is 12, so 12 squared. And that gives me 21.54 meters per second when I reach the bottom. Now, that means when I reach the bottom, I have more centripetal force than I have at the top because I have a greater velocity, but I have the same radius and the same mass. So what we find is the centripetal force between the top and the bottom of these circular paths changes. Okay, so let's try this one here. Now, the 60 kilogram person in the previous example was traveling at 12 meters per second at the top of this 16-meter circular track. And when they got to the bottom, they're traveling at 21.54 meters per second. How much change was there in the normal force acting on the person? Okay, so we've already established in a previous example that the normal force at the top is 480 newtons. I don't want to go back through that, but that's what it was 480 newtons when we calculated before. Now we're going to say is when you reach the bottom, uh, the centripetal force, mv squared over r, is going to be equal to the normal force, which is pointing towards the center, minus mg, which is pointing the opposite way. Now, mg, I happen to know, is 600 because it's a 60 kilogram person, and that's going to be negative. And I can just go ahead and substitute in these values. The mass of the person is 60. The velocity at the bottom we calculated in the previous example, and we have it up here is 21.54 meters per second. The radius is 8. So when I solve this, I'm going to have to add this to this, and I get a lot of normal force at the bottom. So basically, the normal force at the bottom uh, is 4,080, whereas at the top it was 480. So it went up by a factor of, the normal force went up by a factor of 10. What is the minimum velocity the cart needs to have at the position shown in order to complete the loop without falling? Okay, that's a pretty common question they ask. And it's a beautiful question because it combines your understanding of conservation of mechanical energy with your understanding of centripetal force and vertical circular motion. So let's just give this a try. All right, whoa, it looks hard, but it's really not if you think about it. We're going to start where we should with conservation of energy. I'm going to say mechanical energy I start with equals the mechanical energy I end with. There's no springs in this case here, so I can get rid of that. So that tells me, and I'm at the bottom here, so I don't have any gravitational potential energy. So I just have, I have kinetic energy. I have 1 half mv squared is all I have here. And when I get to the top, I've got two things, right? I've got kinetic energy and I've got gravitational potential energy. Now we've established that the minimum velocity you need at the top in order to complete the circle is root gr. Okay, so how much kinetic energy would I have at the top? Well, I have 1 half m uh, uh, square root g square r, square root gr squared. And then the potential energy I have at the top is going to be equal to mg2r. So, as is often the case, those m's just go away, right? So I got rid of all my m's. Now, if I square this, it just becomes 1 half gr plus 2gr. So what that gives me is 2.5 gr equals 1 half the v squared. So the v squared is equal to 5. So therefore, the v is going to be root 5 gr. That's the minimum velocity I need coming into this in order to not fall off when I go to the top. So it's just conservation of energy. I just have to remember to think in terms of radius instead of height. And I have to, in this case, well, I cheated a little bit. I didn't derive this. I just remembered that the minimum velocity is root gr. That was the trick to solving this problem. Last one, I promise. What about these ones? The College Board does like these. They're kind of fun. So when you go over a bump like this, you go over the top. I remember when I was a kid, my Uncle Roy used to take us on this one road really fast in his VW bug, and we go over the top of these, and we become floating out of our seats a little bit. We call them wee bumps because the way we floated up in the air was just kind of fun. Wee! All right. So, and he was a spy too, by the way, just like my dad. Okay, so what is the fastest speed that this car could go without losing contact with the ground? Now, I gave you the mass of the car, but as you could probably figure out, the mass of the car doesn't matter. All right, it's not like the heavy person is going to stay in the seat, the lighter person not. It doesn't work like that at all. So let's just try this. I have a radius, a circular radius to the hill. Okay, and so what I'm going to say is centripetal force is equal to mv squared over r. And now in this case, what's keeping me going in a circular path when I get here? Well, the only thing is gravity. So it's kind of the opposite of what I had before. Instead of what's the slowest I go, it's what's the fastest. Because if I go faster than this, I'm not going to stick to the ground anymore. All right. So gravitation mg is going to supply the centripetal force. Again, the m's cancel out, and lo and behold, what pops out of again? Maximum velocity. In this case, instead of minimum, in this case, it's going to be the maximum velocity. Because if I go any faster than that, then gravity is not going to be able to hold me into a vertical circular path, and I'm going to go flying outwards instead of falling inwards. And so I can just substitute into that, and I can find that 14 meters per second is the fastest I could travel over the top of a hill that's got a 20-meter radius to it and still expect to stay on the ground. And Hollywood loves to have them go faster than go off the ground. Okay, thanks for watching this. Sorry it was so long. We'll work on this when we get in class tomorrow.